Welcome to Talk Tensors.
Today is going to be a fun one. We're looking at the paper that basically taught AI how to hallucinate in a responsible way.
I want to start with a little thought experiment.
Yeah.
Imagine I lock you in a room. In one corner, there's a giant stack of books, all in English.
Okay, a standard setup.
And in the other corner, a giant stack of books, all in French. But here's the catch.
There's always a catch.
No dictionary, no Rosetta Stone, and not a single book exists in both languages. You've got, say, Harry Potter in English, but only Les Miserables in French. Zero overlap.
So you have two completely disconnected piles of data. That's a nightmare for a translator. You have all the material, but no bridge between them.
Exactly. And your job is to learn how to translate between them. I mean, intuitively, that feels impossible, right? How can you map a word if you've never seen it paired with its partner?
Well, in the world of supervised machine learning, the world we were mostly living in before 2017, you're right, it is impossible. You need that answer key. But today's deep dive is on the seminal paper that proved you can solve this if you just follow one very, very clever rule.
We are talking about unpaired image-to-image translation using cycle-consistent adversarial networks.
Or as pretty much everyone knows it, CycleGAN.
Right.
This paper was an absolute bombshell when it dropped at ICCV in 2017. It really changed the fundamental economics of generative AI.
Economics, that's an interesting way to put it. You mean the cost of just getting the data?
Exactly, the cost of data. Before CycleGAN, if you wanted an AI to turn, say, a black and white photo into a color one, you needed paired data.
Paired, so a perfect one-to-one match.
Right. For example, to train a model to turn a sketch of a shoe into a photo of a shoe, you needed a data set with the photo and then the exact line drawing of that specific shoe. Thousands of them.
We've talked about this with Pix2Pix before. That was the predecessor, and it was brilliant, but it was just so needy. It had to have those aligned pairs.
And that's a massive, massive bottleneck because in the real world, paired data is rare. It's expensive. Sometimes it's just physically impossible to get.
But trying to get a CT scan and an MRI of a patient at the exact same time.
You can't do it, but unpaired data, that's everywhere. It's free. We have millions of photos of horses online. We have millions of photos of zebras.
But we definitely don't have a photo of a horse standing in the exact same pose with the same lighting as a zebra.
Right. You can't just ask the horse to hold still while you touch stripes on it. So the thesis of this paper and why it's a classic is that they found a way to learn this translation without ever seeing a direct match. They proved that by enforcing what they call cycle consistency, you can translate between two totally separate domains.
Okay, so let's get into the mechanics. How on earth do you teach a machine horse to zebra if it's never seen them side by side? It sounds a bit like magic.
It does, but it's really just a very clever trick in how you structure the problem. You're basically tricking the model into teaching itself. The architecture isn't just one network, it's two GANs, two generative adversarial networks working in a loop.
So let's break down the players here. You said two mappings.
Correct. Let's call them mapping G and mapping F. So G is your forward translator. It takes an image from domain X, let's say our horse, and tries to turn it into domain Y, a zebra.
And F is the inverse. It takes a zebra and tries to turn it back into a horse.
Exactly. Now, in a normal GAN, you also have a discriminator, right? Its job is to be the critic.
The art critic.
So you have a zebra discriminator. It looks at the output from mapping G and just asks one question. Does this look like a real zebra?
So it's checking for stripes, mane shape, that kind of thing.
Right. It has no idea what the original horse looked like. It just cares if the forgery is good enough to pass as a zebra.
But if that's all you have, couldn't the model just cheat?
It absolutely would. This is the classic mode collapse problem. If I'm the generator and my only goal is to make the discriminator say, yep, that's a zebra, I could just find one perfect picture of a zebra
and turn every single horse I see into that exact same picture.
Exactly. I feed in a pony, I get generic zebra A. I feed in a Clydesdale, I get generic zebra A. The discriminator is happy, but the translation is a total failure. You've lost all the information from the original.
Because there's nothing tying the output to the input structure. The discriminator just says, nice zebra, not nice zebra that's standing in the same spot as the horse was.
Right. And that's where the big idea comes in, the cycle consistency loss. This is the cycle in CycleGAN.
This is the core innovation.
It creates the structured loop. The authors use this great analogy from Mark Twain. If you translate a sentence from English to French, and then you translate that French sentence back into English, you should end up with what you started with.
I remember that story. He translated a French version of his own story back into English, and it was just complete gibberish.
They actually cite that story in the paper. It's the perfect example of broken cycle. So what they enforce mathematically is this. 6 to G, X to GX should be approximately equal to $6.
Okay, walk me through that with the animals.
You take a real photo of a horse, that's $6. You feed it into the generator G to get a fake zebra. Then, and this is the key part, you take that fake zebra and you feed it into the inverse generator F to turn it back into a reconstructed horse.
And that reconstructed horse has to look identical to the one you started with.
Down to the pixel. If the horse's head moved or the grass changed color during its trip to Zebraland, the model gets penalized heavily.
So it forces the generator to preserve all the structural information, the pose, the background, and only change the specific texture that defines a zebra.
That's a great way to put it. It's information preservation, and it works both ways. There's a backward cycle, too, from a real zebra to a fake horse and back to a reconstructed zebra.
So the total score the model is trying to improve is a mix of these things.
Yes. It's the standard adversarial loss fooling the discriminator plus this cycle consistency loss. And they weight that cycle loss really heavily. The lambda value is 10.
10? That feels very specific. What does that mean?
It means the model cares 10 times more about making that round trip successfully than it does about just fooling the discriminator. It's a huge weight that says, I don't care how realistic your zebra looks if I can't turn it back into the original horse.
So that structural preservation is really the main goal.
It is. Oh, and before we move on, there was one other clever little loss they added for the painting experiments, the identity mapping loss.
Ah, yes, the painting trick.
Right. So they were training models to turn photos into Monet paintings. But Monets have these warm sunset tones. The generator started to think, to be a Monet, I have to make everything orange.
So it was turning daytime photos into sunsets.
Yeah, even if the input was already a Monet painting. So they added identity mapping. Basically, if you feed a real Monet into the photo to Monet generator, the model is trained to realize, oh, this is already a Monet, and just leave it alone.
So it teaches the model to not mess with a good thing.
Exactly.
Let's get under the hood with the architecture. They made some specific choices that became pretty standard for this kind of work.
They did. They used an architecture that was originally for style transfer, and the big change there was using instance normalization instead of batch normalization.
Okay, why does that matter? We hear batch norm all the time.
Well, batch norm averages statistics across a whole batch of images to keep training stable. But in style transfer, averaging is bad. It washes out the specific details of an individual image's style.
It's like you're blending all the colors together.
Yeah. Instance norm looks at just one image at a time. It normalizes the contrast based only on that single image, which preserves all those sharp, distinct stylistic details. It's crucial for making a good Van Gogh.
And they also used residual blocks, ResNets.
Yep, 6 or 9 of them, depending on the image size. But the really cool piece of engineering for me was in the discriminator. They used a patch GAN.
I've heard that term. It doesn't look at the whole picture at once, right?
Correct. A standard discriminator gives a single real or fake for the whole image. A 70 by 70 patch GAN, it slides a little window across the image and decides if each 70 by 70 patch is real or fake.
Why is that better?
It forces the generator to get the high frequency details right. It doesn't just care if the overall blob is a horse. It cares if the texture in this tiny corner looks like horse fur. It solves that blurry image problem that a lot of early GANs had.
And it must be a lot faster with fewer parameters.
Much faster. And it can run on any size image, which is a nice bonus.
Okay, let's get to the fun part. The results. I still remember when this paper came out, you couldn't scroll through social media without seeing that GIF of a horse smoothly turning into a zebra.
That was the hello world for this technique. The object transfiguration was stunning. Horse to zebra, apple to orange. But for me, the style transfer stuff was even more amazing.
Taking a photo of Yosemite in the summer and turning it into a snowy winter scene.
And back again, winter to summer. And the art. Taking a normal photo and rendering it in the style of Monet or ukiyo-e woodblock prints. The Monet to photo results were particularly wild because they were generating realistic photos from Impressionist paintings.
Which is way hard. You have to invent details that just aren't there in the painting.
Right. But they didn't just rely on pretty pictures. They ran actual studies on Amazon Mechanical Turk.
This is where they show people the fake image and just ask, is this real?
Yep. For a task translating maps to aerial photos, CycleGAN fooled people about 26.8% of the time.
Is that good? 26% doesn't sound amazing.
In isolation, no. But you have to compare it to the baselines, the other unpaired methods at the time. They were fooling people less than 2% of the time.
Oh, okay. So going from 2% to nearly 27% is a massive leap.
It's an order of magnitude. It showed that this unpaired approach wasn't just a toy anymore, it was getting competitive.
They also used something called an FCN score on the Cityscapes dataset. This seemed like a really smart way to test utility, not just looks.
I loved this test. So Cityscapes is a dataset for self-driving cars. They took the semantic labels, the maps where roads are purple, cars are blue, and had CycleGAN generate realistic street photos from them.
So the AI is drawing a street scene from a map.
Right. Then, to test if that scene was any good, they ran a standard car detection algorithm on the fake photos.
So if the car detector can find a car in the fake photo, the generator did a good job making a car-like object.
Precisely. If it just drew a blue blob, the detector would fail. CycleGAN scored significantly higher than the baselines, getting much closer to the fully supervised upper bound. It was closing that gap.
But we have to talk about the failures. Because as cool as the zebras were, some of the results were a bit disturbing.
The dog-to-cat problem.
Right.
This really shows the core limitation. CycleGAN is great at texture, changing horsehair to zebra stripes. It is terrible at changing geometry.
It can't reshape the object.
Exactly. When they tried to turn a dog into a cat, it didn't shrink the snout or change the ears, it just painted cat fur onto the dog's head.
So you get a dog wearing a very convincing cat costume.
That's a perfect description. And it makes sense, right? If the model shrinks the dog's nose to be a cat nose, how would the backward generator know to grow it back to the original size? It's safer to just leave the shave alone.
And then there was my favorite failure, the writer problem.
This is a classic example of dataset bias. The model was trained on wild horse and wild zebra photos, mostly just animals in nature. It had never seen a human riding a zebra.
So when they fed it a picture of a person on a horse,
it had no idea what a rider was. It just saw this weird shape on the horse's back and assumed it was part of the horse, so it just grafted zebra stripes all over the person.
It's pure nightmare fuel, a zebra-human hybrid.
Terrifying. But it's a great lesson. These models have no semantic understanding. They don't know human or horse. They just know patterns of pixels. If a pixel blob is on the horse, it gets stripes.
Despite the scary results, the legacy of this paper is just undeniable.
Oh, absolutely. It democratized this whole field. Before this, you needed a research budget to label thousands of images. Afterwards, any artist or hobbyist could just download 2 folders of images and start training a model.
It's a huge part of why we have so many sim-to-real applications now in robotics.
Totally. You train a robot arm in a video game because it's safe and cheap. Then you use a CycleGAN-like model to translate the game's visuals into real-world visuals so the robot knows what it's looking at. It's foundational stuff.
It really proved that you don't always need a teacher. Sometimes you just need to be able to check your own work.
If you can translate it back and it still makes sense, you're on the right track.
Which I think brings us to the part of the show where we start checking our work and start speculating wildly. It's time for novel notions.
This is where we take the core idea of the paper and propose some hypothetical, maybe slightly dangerous research ideas.
Okay, I've got one. I'm thinking about mental health. I'm calling it cycle-consistent cognitive filtering, the rose-colored glasses protocol.
Okay, I'm listening.
We use CycleGAN for real-time augmented reality. You train a mapping between, say, high-stress urban environments and calm naturalistic environments, like the Yosemite summer to winter transfer, but on your smart glasses.
So you're walking down a busy street, but you're seeing a peaceful forest. That sounds incredibly dangerous. You'd walk right into a car.
That's where the paper's magic comes in. We enforce a very strict cycle consistency loss as a safety feature.
How does that help?
The transformed view has to be perfectly reconstructible to the original. So if a yellow taxi is speeding towards you, the AR can make it look like a rushing river or breezy cloud. But the underlying physics, the trajectory, the velocity, the size, has to be identical. Right. G must equal 6 dollars.
I see. So the semantic content, large object on collision course, is preserved by the cycle constraint. You still dodge the cloud, but the aesthetic stressor of the city is gone.
Exactly. You react to the physics of the cloud, which is the same as the physics of the car. It's therapy via style transfer with a mathematical safety net.
That is surprisingly profound. Okay, my idea is a bit more biological. Unpaired cross-modality medical hallucination.
Medical hallucination sounds like something we try to avoid.
Hear me out. In medicine, we have tons of unpaired data. We have millions of audio recordings of coughs. We have millions of MRI scans of lungs.
but almost never a cough and an MRI from the exact same person at the exact same moment. The classic problem.
Precisely. So we trained a CycleGAN to translate audio waveforms directly into MRI image data.
You want to generate a lung scan from the sound of a cough.
Yes. You force the model to hallucinate the lung structure that would have produced that specific sound.
How do you know it's right?
The backward cycle. The generated MRI, when you translate it back to audio, must sound exactly like the patient's original cough. You use the sound to constrain the geometry.
So if the model fakes a healthy lung MRI, but the cough had a wheeze, the backward audio translation would be clean and the cycle loss would punish it.
Exactly. It forces the model to learn the latent physical connection between lung volume, which it sees in the MRI, and acoustic resonance, which it hears, without ever being told how they connect.
That is wildly ambitious. If it worked, you could do a preliminary screening over a phone call.
Or get a very, very statistically probable hallucination of one.
Just to be clear to our listeners, do not try to diagnose yourself in the CycleGAN. This is for entertainment only.
Please see a doctor, not a discriminator.
Well, whether you're turning horses into zebras or coughs into lung scans, the lesson of CycleGAN is clear. Sometimes the best way to understand a translation is to translate it back and see if you lost anything.
If you can find your way home, you probably know where you are.
If you want to see the original paper and all the slightly terrifying results, check the link in the description.
It's absolutely worth a read.
This has been Talk Tensors.
See you in the next cycle.